But usually.
Should we start over?
Yeah.
All right. Yeah, this is introduction to natural language processing. I'm Kejin.
And I'm Kausthubh. Okay, so in this workshop, we're going to do the basics of natural language processing in the context of healthcare applications, 7 different ways to capture semantic meaning of text. Okay, so what is natural language processing? So it's just a discipline of artificial intelligence where you can use computers to understand and process and generate human language. And so I copied a quote from a Medium article that kind of best summarizes NLP, where it says that natural language processing is mainly about filling the gap between how humans communicate with natural languages, such as English, and what computers understand, machine language. When this task will be fully solved, you'll be able to communicate with a computer or your tablet, cell phone, or your smart refrigerator in your car, just as you do with any other human being. So we can train machines to perform tasks on human language. So we can perform tasks such as machine translation, which is like Google Translate. You can translate from English to Spanish. Information retrieval, so retrieve like documents that fit the needs that you are kind of querying for. Language generation, which is things like tools you have used like ChatGPT or Claude. And language analysis, which can be tagging sentences with the part of speech or doing named entity recognition. So some examples of things you may have interacted with are things like ChatGPT, Google Translate, or Smart Alexa. These all are based on natural language processing techniques, or they use transformers. They used preprocessing techniques like text processing and morphological analysis to create these tools that you interact with. And these same techniques can also be used to perform classification tasks or any other language-based tasks that you may need to do for your own research or for your own work.
Okay, next we'll cover is basic text preprocessing. So if we just give the computer like a string of words, it's not going to interpret that. So you want to break it down into a format where it can. So preprocessing is often the important first step. And we want to modify so we can get clean standardized text so the computer can easily perform whatever it wants to do. So typically what happens is the document is first broken down into small units, which are called tokens, and a process called tokenization. So the process usually goes from documents, separate to sentences, separate to tokens. But tokens can be very ambiguous. Before you pre-process anything, you can your token can be defined as anything. So most simply, people do it with words. So words is often what is the smallest unit that holds meaning in the English language. So these words. Some places also use letters. This is for English, but if you have like other ones like Chinese or anything else, your tokens might also be a little bit different. Another issue is that even for English, it can be very ambiguous. It's like if you have the word like self-driving, which is hyphenated, or don't. Are you supposed to break this into 2 tokens or 1 token? Because self-driving, obviously, these two are connected. Don't, it's do not, it's the same issue. Same in places like exclamation marks or punctuation, or abbreviations like NYC. You want to separate to N, Y, and C, or just that thing. And there's also suffixes too, prefixes and suffixes. There's many different ways to tokenize text. This workshop will use a package called Spacie. And yeah, if you want to see example, if I were to tokenize a sentence with Spacie, it becomes this. It just separates each one into individual words. In this case, don't get separated to do and not. Next. Okay, so after tokenization, there's many other pre-processing steps. We'll just go over some very simple ones. One example is normalization, which is either through lowercasing or uppercasing. So usually, most times you will lowercase everything. So what it does is all your tokens become lowercase. However, there's obviously pros and cons associated with it. Some pros are it reduces the total amount of vocabulary in the document, because if you make everything lowercase, if it's like the start of a sentence or something in all caps, it becomes the same word. And it boosts efficiency because the smaller vocab space. Like if I were to search for word, because there are less things, it's faster to get it. However, it can lead to information loss because if you have a proper noun and some other word, it will become the same thing. Like an example, you becomes you, which is fine. Go becomes go, but I have may, like I may do something, which becomes may. And also maybe the month may or the day may, that becomes the same may. So if you do that, you lose information. Another thing is stop removal. So stop removal is removing things that are very common occurring, but carry very little meaning. So often these words are like the, this, just very filler words that come into a sentence or conversation. Like if you take it out, you'll be fine not having it. So like case folding, it also reduces the vocabulary space, reduces efficiency, but this can affect the context. If you have a very simple sentence like, I like food, which becomes like food, which keeps the same meaning. But if you have something like, I did not like the restaurant, it will take out I and not. So it becomes, and also I did not. So it becomes like restaurant, which is very different than the original sentence here. And also stop words is, there's no universal list. You can make your own, or you can use built-in ones. So Spacey has a built-in one, which we'll use, but many people use their own depending on what they're trying to do. Next is, these two are very related, stemming and lemmatization. So stemming involves removing the prefixes and suffixes of words. Usually these things like running, runs, like it's often the same words, it's just run with something added to it. This is usually done through algorithm. Well, this is for stemming. The most famous one is called the Porter stemming algorithm or Porter stemmer. This guy called Porter pretty much dedicated his entire life to making a stemming algorithm, and that's what people use. Like other ones, the main benefit is that reduces the vocabulary space. And if you have unseen words, you can use it with other known words that are similar. Like if a document is running and someone has runs, both become run. However, there's errors in stemming. There's something called overstemming, understemming, which is where it will stem too much or too little. Like if it's runs and runs, that's fine. But if it's university and universe, they might both stem to universe without where there's no E at the end or no ITY. Obviously, university and universe are different things. So a thing that's been created as like a more sophisticated thing is called lemmatization. Actually, Spacey only offers lemmatization, not stemming, because of the better benefits. So what lemmatization does is it makes every word become the dictionary form of the lemma of it. Yeah, so similar pros. The cons are it can remove slight meanings. When we show you the examples on Colab, like I tried finding it where it doesn't work, but it turns out it pretty much works every time. Like example I thought of was if you have drink and left, it might keep it as drink and left instead of doing it as drink and leave. For left, like maybe it was left side, so they kept it as left, but it actually meant like he left to go somewhere else, so it should become leave. But honestly, like I don't think there's many issues with lemmatization.
All right. So the next part is the text representations. So we're going to go from statistical methods to neural methods. So the first thing is that how do you represent text? We can represent text by using embeddings. And so when we want to kind of describe what a word is, we can use different relations. So we can use its synonym relations, its similarity, the association of a word, and also the connotation. So the question is, how can we represent the meaning of a word that also allows us to relate to other words? So the answer that we use in NLP is a word vector or embedding that can represent the semantic meaning of a word. And so in a vector space, we can have a vector of the word, and the vector kind of has a semantic, represents semantic meaning in a way where you can take the cosine similarity of two vectors and get a value that represents its similarity. So the cosine similarity of helicopter and drone will be greater than helicopter and bee, for example. And so this is a big advantage of using vectors to represent words. So I'm going to cover three different ways for how to generate these vectors to represent words or documents in a way to kind of keep the meaning and to perform downstream tasks. And the first method would be term frequency inverse document frequency, or is known as TF-IDF. So in this case, we're generating embeddings that do not, we're generating embeddings using the statistical frequency of a word in a corpus. So corpus is just a bunch of documents with text, and we're only generating embeddings not based on the context of the word, but rather statistical frequency of the words. And it does not generate word vectors, but rather it will create, it will not generate word vectors that represent semantic meaning of the word. And the embedding is generated for the entire document of words rather than the individual words. So, the result of using this process is we get for each document a vector of n length, where n is the total number of unique words in a corpus, and then that vector will be assigned to each document. And that vector will just be like the frequency of each word within that document. So for example, we have three documents, right? One says his name is Peter, second one says Peter got his dog, and third one says his dog is cute. So what we first do is that we want to first perform the TF step, which is called the term frequency step. So each document is represented by a vector of length n, where n is the number of unique words in the corpus. And so in the example right here, we have 7 unique words. So first one to count is the term frequency, where each word is assigned the frequency appears in the individual document, but not the overall corpus. So right here, we have from a 0.25 for each document, because if we go back, we see that each word only appears once in each document. So this would be 0.25. Then we'll perform the inverse document frequency. The issue is that if there's a frequent word such as like A appears several times within a document, right? So we can apply the inverse document frequency to kind of normalize this kind of frequency. So we count the number of documents the word appears in, then we take the total number of documents, and then we compute the IDF value, which is going to be the total number of documents divided by the number of documents the word appears in. And so this can inverse the frequency that the word appears in each document. And so, for example, the IDF for some of the words are, for example, Peter. Peter appears in only 2 of the 3 documents, so we get 1.5. But then the word his is more common in the corpus. We get that value, we get that word 3 times in the total of 3 documents. So we get an IDF value of 1. So then we want to compute the W value, which is going to be the value that we're going to use in our vector for each document. And so that'll just be the TF value times the IDF value. And so for the word Peter, we're just going to do 1.5 times the term frequency value, which is 0.25, and we get 0.375. And so we repeat this for every single word that appears within the corpus. And then we would create a vector using this value of the W value. So for a large corpus, the issue is that we would have a high number of unique words, right? So we'd have very, very large vectors for each document. This would create sparsity, because like if you would have like 1,000 length vector for each document, but each document only has like a total of like 100 unique words, you're going to have 900 elements within the vector just being 0. But what we can do is if we take a natural log of the TF value and the IDF value, so that it would just normalize and smooth the value so it's not too extreme in the vector. And again, the issue with the method is that we still get a sparse vector, but this method is very simple and it can perform well on document classification. So when we go in the Colab notebook, where we download these different methods, we'll see that this will run really fast. It will get a adequate performance, but it does not get the contextual meaning of words. It lacks a contextual semantic understanding for words. So then the next method I'll go over next is word2vec. This one will produce vectors for each word compared to TF-IDF. And so it will also produce dense vectors. So this solves the previous issue of sparse vectors. So this is better if you want to use vectors in machine learning, because we don't have to worry about the sparsity, which could affect the learning process. And word2vec actually does learn the semantic meaning of words. So again, we will also get vectors that capture the semantic meaning of words. And instead of doing a statistical measure of the word frequency, word2vec uses an unsupervised learning algorithm to determine the word vectors. So I'm going to break this down as to what this unsupervised learning algorithm is and how it learns the word vectors. But essentially, this learning algorithm will create a word vector that is a static embedding, meaning that that same vector is used for the word, no matter what context the word is in. Um, so there's multiple ways the word2vec will learn the vector representation. There's two ways: the skipgram and continuous bag of words. So I here have a graph of a figure showing you these two different learning processes. The first one will take the neighboring words of our target word. It will then use it in our unsupervised learning algorithm, and then it will then generate this the one hot encoding vector representing the word we're targeting. Um, and then the skipgram will just take the word we're targeting, we'll take the one hot encoding representing that word vector, and then we'll give it to a learning algorithm, and it should produce the neighboring words of the word. So how does this learning algorithm work? We're going to focus only on skipgram for this example. So for example, if we're going to take we're going to only use, we're going to generate a vector of word W using only the neighborhood of the two nearest words. So we have the sentence, the hotel room's view is stunning. We're going to target the word room to generate that embedding, and we're going to use the neighbor two words. So we're going to use the hotel and view was. Then we're going to train a machine learning classifier. This can be any sort of classifier. It can be a neural network. And we're going to train it. So we're going to be giving it the word W. We're going to be giving it a one hot encoding vector that represents the word W. And then the classifier should then reproduce the neighboring words, which is going to be the hotel and view was. And should return a high probability for those two words being related. But then we also want to make sure that if we give this word to the classifier and we give it some words that are not the neighbors, it should return a low probability of their relatedness. So it should return a high probability of the neighboring words and a low probability for the words that are not their neighbors. Then the question would be, yeah?
So for the word room, we mask that word?
Uh, no, we're not masking it. So masking would be in the example for training BERT. It would be using masking, but in this case, we're just taking the context. We're not guessing what the word room is. We're just taking the word room, and we want to get the neighboring words. We want to have a high probability that those words are the neighbors. So, yeah. So the next question would be that once it finishes classifying, we create a classifier that can predict a high probability of the word room having the neighbor be hotel, for example. Then how do we get the weights? The weights can be simply just computed by using the weights of the neural network performing this classification task. And that can be just be the embedding of the word. And so for neural network architecture looks like this, right? For each hidden layer, you have the weight and then the bias, right? You have WA is the weight and then the bias. You can take the one hot encoding of the vector multiplied by the weight and then sum of the bias for each hidden layer, and you get your embedding, and that will be the embedding for your word. And the objective function of this learning method would be was right here. We're taking the probability of the naming words, and you want to maximize the probability for that word itself. Okay. And so in this case, again, with word2vec, you should just remember that it's going to only generate static embedding. So it'll be the same for a word like car, for example. It will always have the same as like embedding no matter what context it is located in. So this can be an issue. And so next I want to introduce BERT. So BERT stands for bidirectional encoder representation of transformers. So the transformer architecture that has this transformer architecture has the entire text as the context for learning. And BERT is bidirectional, meaning that in a transformer where you have a word, it can use the context of the previous words and later words to then inform to learn and understand the meaning. And BERT is pre-trained on a large corpora using vast language modeling and next sentence prediction task. And so right here, I have a example of what the encoder, this BERT encoder looks like, where you can take two position encodings of the words, and then you have self-attention mechanism. So I'll go over next, where you just think of it as basically as assigning a kind of a value for each context, each neighboring word, to determine like which one is important to learning the meaning of the word. And then you'll get a Z vector, which can be used then for the feed-forward network to perform any sort of task. So first of all, why do we want to use BERT? So the traditional embedding method is word2vec creates static embeddings. So one embedding is generated for a word, and this embedding is used for the word regardless of the context where the word is located. But BERT can create dynamic embeddings where the embedding of a word is not just one value. You can have multiple embeddings for one word, where the embedding it changes depending on the context of the word, right? Because we know that a word's meaning can change if it's in a different context. So BERT uses self-attention mechanism where it can allow for richer contextual representation to generate this contextualized embeddings. So during pre-training, it learns the representation of meanings for words for different contextual settings. And this will improve the performance when fine-tuned for tasks such as question answering, sentiment analysis, and named entity recognition. So this is the overview of the architecture. So right here, I first have the kind of the overall architecture where you have the self-attention layer, then you have feed-forward neural network. And so in this example, you have each word, you have self-attention mechanism where it will for each word, it can look at the neighboring context, like for left and right, and then assign a value for the most important word. So right here is the self-attention mechanism. Example, right now we're trying to generate the embedding for it, for example, right? We can assign a value for the most important words. And so for example, right here, the animal will be like the most important words, and then the lighter values are like less important. To understand the meaning of the word it. And then after self-attention mechanism, we get the Z value, the output value vectors, which can be used in the feed-forward neural network. So I'm going to first cover the self-attention mechanism, like how does this work? So the self-attention mechanism allows each word in the sequence to get to assign the importance to neighboring words. So the first thing you need to understand is there's going to be three vectors that we're going to be looking at. The query vector, which represents the input vector. We then have the key vector, which represents the vector that's used during the self-attention process, and then the value vector, which is the output vector that's used for any task. So we're going to use a learned weighted matrices WQ, WQ, WK, WV that is multiplied by the input word vector to generate the three vectors. So for example, right? So we have right here in the graph, we have two vectors, two embedding vectors, right? So my and name. We'll use a learned matrices to multiply this to get the Q, K, V vectors for each word, right? But now we want to find the context, for example, of word 3. So to find the context of word 3, we want to then multiply the key vector for 3 when multiplied by the query vector of the context word. So for instance, we want to find the context of word 3 with the word 1. We use Q1 times K3. We then want to divide it by the square root of the size of the vector of the input vector to normalize the value. And then we apply the sigmoid function, which basically normalizes to 0 and 1. And so it produces a value that represents the context of the word 3 with this neighboring word 1, for example. So that goes over, I just went over this basic, the first part of attention mechanism. I did reference an article that goes even deeper into self-attention mechanism that covers the second part of the mechanism, and also the feed forward neural network. So if you want to look at that, I have it in the references. But okay, so the next thing is that I want to cover BERT at a higher view or higher level. So like, how does BERT training work? What do we do with BERT? So the first thing is that pre-training BERT. What is pre-training? Pre-training is where we can train BERT to have the contextualized understanding of words, to generate embeddings that can represent the contextual semantic meaning of the words. And so, for example, there's two ways of pre-trained BERT. There is the masked language model, which is basically where we take a sentence, we have a mask for a word, and then BERT should replace the mask with a token that best fills in that gap. So we run this by first giving a sentence. We mask two words, like we mask, there are mask at the dog mask. And then we train it so that eventually produces a token that can that best replaces the mask. And so we want to get the word dogs and park because the best replacements per mask. Another way we can pre-train BERT is that we can use next sentence prediction, which is where we're going to be given pairs of sentences, and the model should predict whether that the pair of sentences are adjacent to each other. So if we're given two sentences, does the first sentence precede the second sentence? That's all it's doing, and it can learn the contextual meaning and generate embeddings. And so in this case, for example, BERT has been trained. BERT is trained over 64 TPUs by Google over 4 days. So, and over like a large data set. And so that level of training gives it a very deep understanding of contextual understanding and to represent words semantically. And so pre-training allows you to use a model that's been trained on a very wide data set of huge context. And you can take that model and then fine-tune it for a more specialized task. So what it's doing is called transfer learning, where you can transfer this learning over a large data set to your more specific task. So it's a lot better than doing your own training of your model, because it's not possible to do your own training of your own transformer, because it requires a lot of resources and a lot of days to do that. So it's why I have a huge advantage of using BERT itself. So once you have a pre-trained BERT, you can download the model weights from Hugging Face or any of these like machine learning repositories. We can download these weights of BERT and we can fine tune to perform some downstream task. So some tasks we can perform is, for example, a name entity recognition, where we are given a set of input tokens, and it will take each token by the specific entity. So for example, it would identify Jensen Huang in a sentence as a person and NVIDIA as an organization. We can also do question answering. So BERT can actually be given a set of input tokens and produce output tokens that can answer this question. And the last thing is that you can also do text summarization. You can take an input of tokens, which is like the text, and then you can produce an output of token, which is like the output of the summary of that text. So the fine-tuning task is you can do a lot of things with BERT. It's very powerful by using this pre-trained knowledge over this data set. Okay, so the last thing I'm going to cover before we go to the demo is applications in healthcare. So,
okay, so first we're going to go over Bayes theorem and naive Bayes. So now you see that we have these vector representation of words. A very simple way to classify things is with naive Bayes. So before that, we'll go over Bayes theorem, which is what it uses. So I'm sure everyone here has probably seen Bayes theorem before. It's based on conditional probability. So if I want to find the probability of having events A and B, it's to be the probability of A times the probability of B given A. Okay, so the given part is because most times things in real life depend on each other. Like there's obviously, you can think of independent things, like if I were to flip two independent coins, those two events be independent, what the results would be. But usually like what happens before is influence what's gonna happen next. Like you have a deck of cards and you want to find the probability of getting two heads without replacement. So the first time some guy draws a card and the second draw, those are dependent events, because if someone draws a head, it's gonna lower the probability. Same with if they don't draw a head. So if we have this relationship based on this probability of P of A and B, we can divide over one of P of A or P of B to get Bayes' theorem, which is equal to what is shown above. So it just means that if you want to find A given B, you can use P of A, P of B, and B given A. Because sometimes those three quantities might be easier to find than the one you're trying to find. So just some language. So for simplification, P of A given B is called the posterior distribution, P of A is called the prior, P of B given A is called the likelihood, and P of B is the normalizing constant. So essentially what Bayes' theorem is, once we go over it, is as you get more information, you can update your beliefs and make a better judgment of what you think it will be. So what does naive Bayes do? Naive Bayes just wants to find something that will maximize your posterior distribution. So for our sake of our example, let's say A is the class and B is the document. That means if you give it a document, you want to find what class is it most likely going to be. So that's our question we're trying to find is P of class given document. But this is a little bit harder to find than if we were to find the other three elements. So let's look at the likelihood, which is P of B given A, or the document given the class. So obviously, if you just have the entire document, it's hard to really give it like a certain number or like a value. But as we showed before with the vectorization of words and everything, we can also make an assumption that all the words in the document are independent. So once we make them independent, we can split the document into each of the individual words. And the individual words, we can transform it into some sort of weight based on what we did before, and you'll get a vector of weights for each of the individual words. And then as you remember from before, if these are normalized vectors, if the dot product is close to 1, they're very similar. If it's close to 0, it's not similar. It's going to be between 0 and 1 because all the weights are between 0 and 1. So that's what this step is doing here. We're splitting up into words, and then we're going to multiply each of the conditional probabilities. So that will give us our likelihood. For the normalizing constant, we can pretty much ignore it because it's just whatever the probability of the target document class is, which is going to be the same for everything because it's just one document class, one target document. And then P of A, which is the probability of the class, you just find all the classes and then find how many of your target class you have over the total amount of classes. So essentially your maximization problem is you want to maximize this quantity here, which is the probability of the class, which is pretty easy to find. Whatever, how many classes you have over the total number times this likelihood that we simplified into. Once we, this is not a probability because we're going to divide by normalization constant. Also, I would not think of this as probability. It's just a metric that you can use to determine which is the most likely. So once we have our document, our class, just try all the different classes you have and see which one of these is the largest. And then whatever you have there is the one you're going to classify it as. And this thing is used in many different things. One way is k-nearest neighbors. You take the nearest neighbors of it. So you take a point, you find the k-nearest neighbors. Of those nearest neighbors, whatever is the most likely is what you take, which is an application of you would use naive Bayes or Bayes theorem.
All right. So next we'll cover some of the applications you can use this like NLP in healthcare. So again, you can use this for name entity recognition to identify when reading clinical notes, you can identify these diseases. You can do symptoms and medical text. Another popular tool is decision support, where you can do medical question answering. So you can generate answers to clinical questions. Using knowledge graphs is built on medical literature. Nothing else with patient care. So some use chatbots to help answer questions or to support for appointment scheduling. So when trying to perform these tasks, pre-trained models is a really helpful way to perform these tasks because again, training your own model on large data sets is very difficult and can be sometimes unfeasible. And so again, there's some popular pre-trained models such as like BioWordVec, which is a word-to-vec model that's trained on PubMed and MIC3 clinic notes using fast text. Fast text is like a Facebook released library. It's kind of like a modified version of word2vec, but this will have a better understanding of clinical terms and healthcare terms compared to a standard word2vec model that you would use. So I think that I didn't mention when covering the embedding models is something called the out of vocabulary problem, which is where if a model encounters a out of vocabulary word, one of the things it can do is it can apply morphological analysis. So for example, let's say it encounters a word running. You could split running into run and ing, and it may know what run is and what ing is. But in this case, when you're doing with medical applications, you can be dealing with like clinical codes, like such as like a clinical codes can be like a word where it's like a mixture of letters and numbers, or you can be dealing with like specific terminology that the model may not be trained on, and it may have to deal with this out of vocabulary words, and it will get poor performance when doing these fine tuned tasks. So another example would be MedBERT, which is a BERT model, but is also pre-trained on structured EHR data from this many patients. And so it has better contextualized understanding to actually understand clinical codes, and can be used for disease prediction tasks. So for example, if you're doing research or if you're working for a company and you're being asked to perform any like classification task or any fine-tuned task, it is really important to consider what data sets you're working with. What are the cases you should consider for? What are the extreme cases you should consider for? And evaluate the different pre-trained models that exist and also the data sets that they're trained on to ensure that you're not going to be dealing with any sort of issues that may hurt the performance of the model. All right. So the last one to cover is just a demo. We have a Colab notebook that kind of demonstrates how to implement the models. If you wanted to access it, you can just type in the link right here or just get a QR code that will get you the Colab notebook. The GitHub will have a README page, will has the Colab notebook link, and you can access it from there. All right. I'm going to switch over to the Colab notebook. So the first thing is that we're going to be using a repository from Kaggle, which is a clinical notes that is labeled for the different specialties that they come from. And so we downloaded that right here. It comes as a CSV where you have the file name, the content of the file, which is the clinical notes, and the label of where the notes, what department the notes come from. And then we just create a label, and then
If you want to keep up,
yeah.
Yeah, so if you want to import it, just import Spacey. And then this download here is just something where there's like a collection of documents, articles, and they did a lot of the pre-processing stuff on it. So you have a lot of things we went over, like software removal, like other things like that. It's already done for you. So you can use this one to make a really quick and simple NLP model. Okay, so if you want to create it, just basically upload, and then the thing we downloaded there, the pre-trained things. So the first step is tokenization. So you just gotta give it an example string. So these are some sample things I made, and then we're going to tokenize them. So how you make it is you're gonna do NLP, and then you're gonna call onto the sample sense you made, and then it's gonna become a doc object. That's why these things are called that's why labeled as doc1, doc2. So a doc object, it's kind of like an array, like it's a collection of items. Each of the items inside is a token. And then if you were to splice many of them together, you would get a span of objects. So if you want to access things, it's kind of like accessing stuff in an array. If you see here, what's inside a doc, so this would be the first element inside the first doc. It's the class is a Spacey token. If you were to iterate over it, it's kind of like iterating over a string. It just gets you each of the individual tokens. So like we did before, can't became cannot. Everything else just got separated by some words. And then slicing is just taking the first two elements. The last one is non-inclusive. So the first two, which would be this and workshop. So these are doc objects. And then there's some other features here. You can call the doc. So doc.token.text is the text, token.I is the index of the text. So like if you see here, this is position 0. That's why it's 0 here. Go to like natural, this is index 4. So that's what it is. And lastly, the property about doc objects is that it's non-destructive. That means if you have a doc object, you can always recover the original text you inputted. So if I do doc.text, this will just give me what I have for the string that I put in. So these are some examples with 2 sample sentences, just breaking the tokens and giving you indexes. Now we go to normalization. So for normalization, the method you're going to use to call it is going to be dot lower underscore. So it's kind of the same thing. You're iterating through an array, so that's why there's the token one dot lower for token one and doc one. And then what it does is it lowercase everything. So if you look here, natural language processing was all in capitals, now it's all lowercase. Same with the first word of each sentence, which I capitalized. Like we said before, there's going to be issues that will happen with lowercasing. So like in this case, I made a sample sentence that will show it. Another sentence, this was President Bush likes to look at the bush in the White House garden. So President Bush, that bush would be lowercase into the same bush as the bushes outside. And then White House is going to be both become lowercase, so you're going to lose the proper noun for it. So next, we're going over is just stopper removal, the same thing. So with the thing we loaded before, it has a stopper removal already built in. If you look at it, those are all the stoppers that they have. And total, there's 326 of them. Like, just very basic ones like what, for, no, as, else. Some other ones here that you might not think of stop words like 8 or 15 or whatever. Maybe because it's words. So yeah, if we were to take out all the stoppers from our sample sentences, you should probably still be able to understand what is going on. So the first one, it goes workshop, natural language processing. So it probably just means it's a workshop on natural language processing, which is what the sentence was saying. The second one is thanks coming, hope enjoying. So yeah, thanks you for coming, hope you're enjoying. And then like I said before, there's potential issues, like this case here. The sentence is we did not enjoy the visit to the zoo. Well, he did not enjoy the visit to the zoo, which becomes enjoy visit zoo, which is obviously very different than what the sentence intended. The last step is lemmatization. This method is just dot lemma underscore. Same way you would pronounce stuff as before. It just makes everything into dictionary form. If you notice, something that I didn't know before is becomes be. Everything else should be pretty straightforward. Like coming becomes come. Since natural is capitalized, it just becomes capital natural. If it's lowercase, it becomes lowercase natural. Everything seems to be pretty straightforward. I was trying to find issues like what we mentioned before, but honestly, every time I tried using it, it became what it was intended. Like in this example here, I used he left the right side of the classroom to go to the left side. I thought they would keep both the lefts the same because one is to leave, one is like the left side, but it correctly say this is leave and this is left. So I guess, yeah, I think this one does not, you can't really encounter that many issues with it. Okay, and then next up we did embedding, also for preprocessing text. So just for the sake of, did you subset this or no?
Yeah.
Okay, so yeah, because of the sake of training, we took a subset of the original training data set, because if we were to call it, it would take like almost 10 minutes. Just shorten it. If you want to do the whole thing, you don't have to do any of the subsetting. And we pre-process the text using what we learned before. So this basic function just pre-process all the text based on what we did before. So if you want to pre-process a column in a data frame, we have political subset. We're going to take this content column here and we're going to apply the pre-processing stuff we have here. And then we just call it pre-process content because the original was called content. And then if you look at the head of the column with just these two columns, you see there's some slight modifications already. Everything is lowercase, the stoppers are removed. If you want a more detailed view, I printed the first sentence of the content and the process content out. So they look pretty similar and you should probably be able to get the same meaning. If we applied more advanced or more pre-processing, we could probably remove some of the unnecessary stuff, like maybe like the greater than and less than signs and other things like that. But overall, it's pre-processed. As you can see, this is a lot shorter than the first one.
All right. So once you're doing the pre-processing, we can then do these several embedding methods. So the goal is that we want to get embedding so that we can then classify each document for the class of the department. So we want to classify one text to be from neurology or one from radiology or gastro. So we're going to first try the TF-IDF method, which is the simplest and fastest way to do embeddings. So this one is pretty simple because if you use scikit-learn, they already have their own TF-ID vectorizer. And so we can do the train test split. We're going to stratify, so we're going to make sure we have the equal number of each label and the test set and the train set. We're going to do an 80-20 split. And then we're going to create the vectorizer where we have our max features. We're going to have the max size of the vector be 5,000. Because again, like I mentioned to you, when you have a large corpora, you can have very, very sparse and large vectors. And so then sometimes you want to limit those like the vector length. You would then fit transform, and then you want to transform using on the train and test set. And then now we have the embedding for each document and the train set and the test set. Then we can apply the multinomial naive Bayes classifier, which is basically just going to apply what we covered in the slides, but to now then classify each embedding to a certain class. And we'll do that and with the predictions, and we're going to get a results. We get 30% accuracy, which is not very high, but actually it's pretty good considering how simplistic TF-IDF is. It's a very simple method. It does not get any semantic meanings or functional meanings. And it's very fast, and we're only using a subset of the data. So if we use the entire data set, we're going to get a higher accuracy, but only using a subset of data, we get a pretty high accuracy. Then we can go towards Word2Vec. So we had to install Hugging Face, a hub, because we want to download the weights of the Word2Vec model. We're going to use FastText, which is like a different version of Word2Vec that's made by Facebook. So we're going to download FastText English vectors. We're going to then load the model using this model path. So this is all downloaded. We're going to have a function right here where we're going to be taking the text of the document using the model. We're going to split the text into tokens, generate the embeddings for each token, and then return the mean of the embeddings. Return an average of the embeddings within the document to kind of get the average meaning for the document. Then we're going to generate X and Y. And then similarly right here, we're going to then do you're going to use train test split using SVC to then classify each embedding into a certain class and make predictions. You can see right here we have a very, very low accuracy. We got 37% accuracy. It's a lot lower than TF-IDF, which made me surprising because, like I mentioned in the slides, is that TF-IDF is a more simplistic version and it doesn't maintain the meanings, right? So the question of why does this happen? First thing I mentioned was that when you're doing certain specific applications of these models, you want to use models that is trained for the specific application. In this case, you may notice that we only use this FastText English vectors model when I didn't mention that there's also this there's a medical Word2Vec model. I didn't use it because first of all, I want to do everything in Colab, and Colab is really difficult to install and download those weights for the medical Word2Vec model. And so a challenge for you if you want to try learn this on your own, try replacing this, try downloading the notebook into your local computer, and try replacing it with the model I mentioned in the slides, and download it and try running it again and see if the accuracy improves. Because that way it would have the contextual understanding for medical applications. Second thing is that in this case, we're focusing more on embeddings, and taking an average of the overall embeddings of a document is not the best approach because it cannot retain the entire overall meaning of the document itself. So that's the things that kind of goes wrong with this kind of method. The last thing I want to cover is BERT. So we use this normal, regular BERT that's not been trained on medical knowledge. So we're going to get the BERT tokenizer and the model. So that's going to be downloaded. And then we have a function to get the BERT embeddings. And so in this case, it's a little more confusing than the previous Word2Vec model because we're taking the text, or tokenizing text. And important thing you should note right here is that when you use a tokenizer, the BERT tokenizer, it will separate each token in the text. But when you're using BERT, the maximum length that BERT allows is 512. So anything past 512 tokens, it can't be used. That's the maximum length that BERT allows in the input for the model. So essentially right here, we're saying that truncation equals true, meaning that any text within our document that exceeds the 512 token is being truncated and not being used by the model. That's just being thrown out. We're only using the first 512 tokens in the text. So this is not a best approach right? To truncate it. What you want to do is you would try to want to generate chunks. So you want to chunk your document into certain lengths. But sometimes the max length will not return the best output. Maybe chunking it to be like 256 or 128. And then generating embeddings over that chunked text might be better than doing it overall. And that can get better results. So we're going to we're going to generate the embeddings. So we're going to use the CLS tokens representation as a document vector. So what is CLS token? So I didn't cover this when I covered BERT. So if you go right here, when you have a BERT encoder, at the beginning and the end of sentence, you're going to have a CLS token. The CLS token represents the start and the end of the sentence. And when you run a BERT on pre-training, it will generate an embedding for the CLS token. And then embedding can be thought of as like a representation of the overall document itself. And so we can take the first embedding generated from the entire document, right? The entire input sequence. So for example, right before there, you're gonna CLS. Right before there, you're gonna CLS, and then you're gonna CLS right here, the embedding right here for the CLS. And you can use it to represent the entire document itself. And so that's what all we're doing right here. So we're gonna run the model, we're gonna get the embeddings. We're going to take the CLS embedding, which is going to be the first token that's from the inputs, and we're going to return that embedding as a vector for each text. So that's what we're writing. We're going to get the X, which is going to be the embedding for each document, and then Y is the subset. So is a label numeric. So we run this, it will run the embedding for each document, and then we use SCC again, and it will then produce the results. As you can see, it's better than Word2Vec, but it's still pretty bad. I'll cover this later as to why it's bad. But next I'm going to cover is the PubMed BERT, which is going to be BERT that's trained on is BERT that is trained on the medical PubMed data papers. So we create a tokenizer model, do the same function as well, generate embeddings, same thing. We do SEC, we fit it, predicted. It does worse than the previous BERT. Okay, so why does it do pretty bad? So the results is because we focus on embeddings, we differential like how to generate embeddings, but BERT can be used to do fine-tuning. We can fine-tune it to perform tasks. In this case, we can fine-tune it and train it on a test set, in a train set to perform a task of the classification of the text to perform to label it for certain classes. In this case, only using the overall embedding does not perform the best results. In this case, using TF-IDF is the best approach if you want to classify text by using embeddings. But when using BERT, you want to use the PubMed BERT and you want to fine-tune it to perform the classification task itself. And I think this is it for the workshop. Is there any questions? Okay. Good. Any
Thank you for
questions?
coming.